So I'm going to get started. So hopefully you're aware there is an exam tomorrow night, 7 to 9 p.m. in Chem 140. Guys, so we'll cover up through the end of Chapter 6, but I might get a little past that in today's lecture, but any material from Chapter 7 is not fair game for this exam. Okay, and then since we're finishing Chapter 6 today, the sapling for that is due next Monday at 9 a.m. Okay, any questions about that? Okay, if you weren't able to make it to the exam review session yesterday, people had some really good questions. The recording should be posted. I haven't checked yet, but you may want to look at that if you want some help with how to solve problems that might show up on there. Okay, so we got about a page and a half of Chapter 6 left to cover. Okay, so far we've looked at asymmetric carbons pretty heavily in this chapter. One sort of interesting topic that we're going to look at real briefly is chirality without asymmetric carbons. So if you remember, a stereocenter is any place where you can swap two groups and make a different molecule. So any place where swapping two groups gives a different structure. Okay, so the two types of stereocenter we've seen so far are asymmetric carbons. That's probably the most common. We've also seen another type of stereocenter, which is any kind of double bond with EZ stereoisomerism on it. What we're going to look at here is a third kind that doesn't fit into either of these categories. Okay, so a real common sort of pattern here is something where the molecule, for whatever reason, ends up with two perpendicular planes coming off of a central carbon. Okay, so there's a few different ways to get this. A real common one is if you have a carbon here in the middle. Remember that for tetrahedral geometry, it has to have, if you show two bonds in plane, then you also have to have one bond going forward, one bond going back. So this is sort of a carbon that's holding together two different four-membered rings, one that's flat in the plane of the board, and one that's perpendicular to that. And I guess really, if I want to be like completely detailed about the geometry, so we're kind of viewing this ring like edge on almost at the square. Okay, so it turns out that if you have the two sides of this ring, like this one has different stuff coming off of it. Maybe if we do, say, H in back, CH3 in front. And on this ring, we have maybe H up, CH3 down. The way to think about this is it's sort of got a handedness to its, like if you're looking down the molecule from this end, I have a methyl that's pointing down and I have a methyl that's pointing out of the board. So if I'm like sighting down the length of the molecule, I would have to follow like a clockwise path as I'm moving backwards. As I'm moving away from me, from this front methyl to this back methyl, I would go clockwise. And that's different from, so if I do a mirror plane, that's different from the other option where Now if I have H the closest to me sticking out of the board, and if I have CH3 closest to me sticking out of the board, and I have CH3 furthest from me sticking down, now if I'm like tracking a path from the front methyl to the back methyl, I have to go from sticking out of the board to down, so I'm going counterclockwise as I pass away from me through the molecule. So think of this sort of like the threading on a screw. Most screws have like one direction of threading, but it's totally possible to have the other direction of threading, and then it won't fit into anything that is designed for like the other-handedness of screw. So we have chirality here. Neither of these is superimposable on their mirror image, but if you look at it, none of the atoms in this molecule are actually asymmetric carbons. Like none of them have R or S that could be assigned to them. Like you're looking at this and you're like, okay, so this has 4 different groups on it. Well, it has 4 groups. It's got an H, it's got a methyl, it's got one direction around the ring, but that looks completely identical to the other direction around the ring. So this is not an asymmetric carbon, but if I pull 2 of the groups off, say the H and the CH3, and I swap them, I'm still getting the other-handedness of twist to this molecule. So it is still a stereocenter, but it's not an asymmetric carbon. And if you're having a really hard time visualizing that, model kits might make the difference there. Try building each of these and then like rotating them around, making sure that you can't superimpose them on one another, but you can still see that they're mirror images of each other. So it's a stereocenter, but not an asymmetric carbon. And then the same for this one out here, of course, because it's got the same stuff going on. So that's another one. And then the hardest one to see, actually, is the central carbon. Sorry, let me finish the sentence real quick. Which it turns out you can do the same thing if you disconnect, say, 2 of the bonds here and swap them. You're basically turning one entire half of the molecule upside down, which would also convert it to the other twist of molecule. Okay, what was your question? But the problem is the other one would end up at the same place, and then it also has an H and a CH3. So at no point do you ever have any way to differentiate between like the 2 groups or the 2 parts that are attached to it. Yeah, so it's kind of like no matter how far out you go, it looks identical, and then eventually it starts wrapping around the other direction onto the ring, and so does the other path. Mm-hmm. Okay, so that's one way to do it. We've got 2 perpendicular planes, and so long as like each plane has different stuff sticking off of it on both sides, so like H versus CH3 here, that's one way to do it. Another way, so it turns out if you've got a carbon with 2 different double bonds coming off of it, one on either side, this is an example of what's called an allene. We'll talk a little bit more about those in OChem 2. But it turns out that one of these double bonds is kind of perpendicular to the other. So like if the pi bond here is sticking out like front and back of the board, the other one will be top and bottom. So if we show like maybe bold CH3 and dashed H here, this one would actually have like its 2 groups be flat in the plane as well. So you've actually got the same deal going on here as you did with the 2 rings up here, where if you're looking from one end of the molecule to another, you have to follow one particular direction of twist as you go from the high priority group at one end to the high priority group at the other end. So this one, if I'm starting here, I'm going from methyl down, and as I go away from me, I'm coming to methyl sticking out of the board, so I'm going counterclockwise to do that. So this would be one direction of twist, and then the mirror image has the other direction of twist, like a right-handed versus a left-handed screw. Okay, so this one also, the 3 carbons that are like in the middle and at the 2 ends of that perpendicular system, these 3 would all count as stereocenters, even though none of them could possibly be an asymmetric carbon. None of them even have 4 total groups attached. So stereocenters, but not asymmetric Cs. And then the third way to set this up is like a combo of these 2 systems, which is the way that I have it shown in the notes, where if you've got like one ring in plane and then a double bond coming off of it, is the same deal. Again, if I follow a path from high priority group in front to high priority group in back, it's got a particular handedness to it. And again, the carbons at both ends and the carbon in the middle all have that thing going on, where you could swap two groups and make it the other handedness. Yeah?
Does that happen where some are perpendicular because it's more energetically favorable? Is it because they aren't being eclipsed? Or?
So it actually has to do with the orbital geometry. So like, excuse me. So the two planes one, that's easiest to see just because carbon has to be tetrahedral, and that's the way it's got to be, like two bonds in plane, one in front, one in back.
That makes sense.
For this one, it helps to remember, so the hybridization on this carbon is going to be what? sp, right? And so it's got two unhybridized p orbitals on it. And so let me actually draw this in. So this one is going to be, so it's got like a p orbital like sticking out front and back. And that's kind of overlapping with this one that's sticking out front and back. So that's one of your pi bonds. And then the other one is sticking out top and bottom, which overlaps with this one sticking out top and bottom. And that's like your other pi bond. So that, I guess it's not because it's energetically, well, it's not really due to like conformational analysis like Newman stuff so much as it is like orbital geometry kind of dictates that. Mm-hmm. Okay, good question. Other questions about how this is set up? Okay, awesome. So yeah, these are kind of the least common type, but they do pop up occasionally. And it's kind of interesting, like, you know, even if you don't have an asymmetric carbon, you can still generate chirality other ways. And there's actually several other ways that you can get chirality going on like a larger scale just by like having a twist in a particular direction versus the other direction, but that still don't involve asymmetric carbons. But this is the only like example or type of example that we'll look at for now. Uh-huh.
Can you just explain one more time how you get the direction of the twist?
Yeah, so what I want to do, kind of like when I was assigning R and S, I want to assign the high priority, damn, sorry, this one's a mess. I'm going to go over here. I'm going to assign the high priority group in the front. So out of methyl versus H, methyl is higher priority. And then I'm going to assign higher priority group in the back. So methyl versus H, methyl is higher priority again. And then I'm going to push away from me, and I'm going to travel from high priority in the front to high priority in the back. So as I go away from me, so methyl is sticking down right now, and it has to rotate to out as I get to the back. So as I do that, I'm spinning my arm clockwise. And so this would be like a clockwise direction of rotation. I don't actually remember what the abbreviation is for the type of chirality where it's got like a twist to it like this. But I think it's like lowercase d and, oh, no, that's not it. Okay, it's two lowercase letters, one for each direction of twist, and I don't remember what they are. Yeah, I don't use this type very often. Like asymmetric carbons are like 90% of what you'll see, and then easy alkenes are like the rest of it. So, okay, other questions about how to do this? Okay, so again, if you're having a hard time seeing it, model kits, just build one of these and play around with it, and it might click more easily. Okay. So, what we're going to look at next is, so we've spent all of this chapter like playing around with model kits and looking at things on like the individual molecular level, but that still doesn't explain like how do we even know about any of this in the first place? Like what are we actually seeing on like a human scale that we would be able to tell if something is chiral or not? So it turns out the really useful tool that we have for looking at chirality is called optical activity. And if you're taking lab, the experiment that you guys do next week actually involves using optical activity to look at chirality of a particular molecule. Okay, so if we've got two enantiomers of each other, they're mirror images, right? And so we'd expect them to have like identical physical properties, like same melting point, boiling point. So pretty much we can't tell the difference between two enantiomers. Like maybe you've got the left-handed version, maybe you've got the right-handed version. They still melt at the same temperature. They still boil at the same temperature. They interact. So ability. They interact with solvents the same, so long as those solvent molecules are also achiral. We'll cover a little bit more about that later on. The only way that we actually have of telling these things apart, if they're mirror images of each other, is how they interact with polarized light. Okay, so I actually, I used to have drawings of how this setup actually works, which I took out of the notes because I thought would be a little behind compared to where we actually are. So I may show these again. They're not actually drawn in the notes, but if you're taking lab, you'll see the exact same drawings in the experiment for next week. Okay, so what this means is that if you have polarized light and you're shining it through a sample of like one-handedness of molecule versus the other, through one enantiomer versus the other, one enantiomer is going to rotate the light in one direction and the other is going to rotate it the other. Okay, so polarized light, you hopefully like have heard of that before, have seen like kind of what it means, but polarized light just means it's vibrating like in a single plane. So normally you have regular light, which is like if it's traveling that direction, there's going to be parts that are like going side to side and parts that are going up and down and parts that are going diagonal or whatever. It's all over the place. Polarized light means it's just vibrating in one plane only. For instance, it's only going up and down. So if you have sort of a source of polarized light over here, and you shine it through a really wonky looking beaker, like some sample of the compound that you're looking at, it's going to rotate the plane of light some direction. So maybe as it travels through here, it'll end up sort of vibrating in a horizontal plane by the time it comes out of the sample. Okay, so as I'm looking down from the end of this thing, I'm going to see the plane sort of rotate from vertical and switch to like horizontal or diagonal as it's coming out of the sample. So it might not flip like this full 90-degree rotation from vertical to horizontal, but we can describe the angle by which it gets rotated. If it got rotated clockwise, which is what we are going to choose to call the positive direction, which is just labeled as plus for short. Then the sample is called dextrorotatory. If it's counterclockwise, which is negative or minus, then it's called levorotatory. Okay, so we actually have this equation that describes exactly like how much it gets rotated based on other factors that are going on. So alpha equals square brackets alpha times C times L. Okay, so that. So alpha is the actual amount that your sample is rotating the light. This is the optical rotation of a particular sample. Square brackets alpha is what's called the specific rotation. And that is going to be a constant for a particular compound at a particular wavelength. And then C is the concentration, like how much stuff you actually have in that beaker. By convention, that's given in grams per milliliter. So it's not really concentration on a molar basis like we're used to using. And then L is the path length. Okay, so concentration, it makes sense that the higher the concentration is, the more the light's going to get rotated because there's more stuff in there to rotate the light. L, also the path length, or how far it has to travel through the sample, it makes sense that the bigger the path length is, the more the light's going to get rotated because it has to pass through more of it to get to the end of the sample. And then the specific rotation, the bigger that is, the more the light is going to get rotated because it's just a more powerful compound at rotating light. Okay, so alpha is what you're actually measuring with our what's called a polarimeter that measures like how far the light gets rotated. And it's dictated by how powerful your stuff is, or in other words, how optically active it is, and then the concentration and the path length. Okay, so for example, say you have a sample with concentration 0.5 grams per milliliter, and you put it in a tube with a path length of, one thing I didn't mention is path length, for whatever reason, is in decimeters, which is the same as 10 centimeters. I think that's just for weird historical reasons. Okay, so it's in a tube with length of 10 centimeters. And you measure an observed optical rotation. It rotating light of 100 degrees. Okay, so you've got some unknown compound. You shove 0.5 grams per mil of it into a tube that's 10 centimeters long, and then you're seeing that as the light's passing up through the tube, the light's getting rotated 100 degrees as that happens. So in that case, 100 degrees equals our mysterious specific rotation times 0.5 grams per milliliter times 1 decimeter. So you should be getting alpha equals, all right, so here's kind of an annoying part. Technically the units on this are 200 degrees times milliliter per gram decimeter. No one actually gives the correct units on specific rotation. They just say 200 degrees. Historical reasons, haha. So it's usually just given in units of degrees, even though there's other stuff that went into calculating that. Okay, so you would say that this has a specific rotation of 200 degrees. And if you are going to be specific about the direction that it rotates the light, say we measure 100 degrees clockwise, that tells you it's plus 100 degrees, which means that your alpha square brackets, your specific rotation is plus 200 degrees, milliliter per gram decimeter. Okay. So that's kind of the gist of how we use this and calculate it. So then the question is, why do we care? So it turns out that the only way to distinguish between two enantiomers is that they'll rotate light the opposite direction from each other. And they also rotate at the same magnitude. So if one enantiomer is alpha equals plus 35 degrees, then the other is minus 35 degrees. So here's an example. This one is R2-butanol, and this one is S2-butanol. Turns out that this one is negative 13.9 degrees is our specific rotation, and this one is therefore positive 13.9 degrees. And so because we have a sign on these, like minus and plus, we can actually include those as part of the name. So we could call this, I'm going to erase a little bit to squeeze in some more stuff, R hyphen minus in parentheses hyphen 2-butanol. And this one I can squeeze in its optical activity as part of the name, S hyphen plus in parentheses hyphen 2-butanol. Okay, so you might see in the name either the absolute configuration, the R or the S, which we figure out from looking at what we know to be the structure of the molecule, or you could see the optical activity, the plus or minus out front of the name, or you could see both, just depending on whether people are giving you more information about how the structure looks or how it behaves like on a physical scale. Okay. So, you may be wondering, like, is S always going to be plus? Is R always going to be minus? Turns out, for a given molecule, if one enantiomer is plus, we know the other is always going to be minus. But we don't know, like, right off the bat. If I just gave you this structure and no other information about either of them, we have no way of looking at the structure and telling this is going to rotate light clockwise or counterclockwise. So I guess that's not 100% true. Like, people are doing computer modeling to sort of figure out, can we predict like which direction it's going to rotate the light once you start like sloshing the electron density around the molecule? Does it have a preference for like one particular handedness of like interaction with the light? But it's not real accurate and great at predicting it. So there's no way to tell, in the absence of any other information, which is plus and which is minus. And so for any given pair of enantiomers, you would actually have to go in the lab and measure it yourself. Or if you know one of them, then you've already got the other figured out. So if your lab mate is like, hey, I've got these two compounds, I measured one of them, it's plus, can you tell me which one it is? The answer is no, I can't. But if they tell you, okay, I have this other bottle over here, it's the same compound, it says R minus, and the one I measured is plus, then you can say, okay, so now I know that you have the S one just because it's the opposite optical activity from the R one over there. Okay. So questions about any of that so far?
Is this fair game on the exams?
I guess as far as, So like doing the math part, no, because like I don't let you guys use calculators. I guess I could phrase a question of like, here's the plus enantiomer, draw the minus enantiomer. But I don't know if there's any good way to set up a question that's not like an immediate gimme if you were like paying attention to the last 5 minutes. So I have to think about that, but probably not. Yeah. Uh-huh. Okay. So any other questions about this part? Yeah.
Will we be expected to include like easy R's when it's not specifically?
Good question. Okay, so what she's asking is, if I ask you to name a compound, do you have to include EZ and RS descriptors if I don't say so? Yes, but I have to be careful about how I would phrase the question, so I might say draw the complete IUPAC name for this structure, and at that point, yeah, you got to include stereochem. But hopefully I'll phrase it a little bit more obviously than that and say like including all stereochemical descriptors, and then you would know you got to have all of them up front at the name. Okay, thank you. So other questions about this part before we move on to the last bit? Yeah. Thank you for that segue. So that's actually the very next part of that I'm going to cover. Okay, so what would happen if you have a mixture of both enantiomers? So this is called a racemic mixture. Okay, so there's actually a cool little bit of history associated with this. The guy who first discovered chirality and optical activity was Louis Pasteur, the same guy who figured out pasteurization and invented Pasteur pipettes. And the way he actually got to samples of enantiomers was there's one particular chemical that it's a mixture of two enantiomers, but when it crystallizes, like all the right-handed ones form little crystals together and all the left-handed ones form little crystals together. And he went through with a magnifying glass and a pair of tweezers and picked out all of the left-handed crystals from the right-handed crystals because they form different shapes. And he put them in solution and got like one of them rotated like one direction, one rotated at the other direction. And then he mixed the two compounds back together in a 1-to-1 ratio, and he found that they didn't actually rotate light at all. So if we mix together an exactly equal 50-50 amount of two enantiomers, basically they're just going to cancel each other out. Like the one-handedness is going to rotate light one direction and the other is going to rotate it right back to where it started. And so it's going to end up not changing the light at all. So it doesn't rotate polarized light. Or in other words, it's optically inactive. Okay, so the compounds that he was looking at actually came out of a batch of wine that had gone bad. And so he chose to name them Racemic, which I think is from Latin for bunch of grapes. So this is called a racemic mixture when it's a 50-50 mix of two enantiomers. All right, so mixing two enantiomers in any other ratio does not count as racemic. It has to be exactly 50-50, so they exactly cancel each other's effects out, so you end up with no light rotation at all. Okay, this is called a racemic mixture, or a racemate. Okay, so in other words, if we have these same two alcohols up here that I showed before, like 50% of the R and 50% of the S, there's a few different ways to label this. One is plus minus 2-butanol, or rack 2-butanol. So technically this isn't just one compound anymore, it's an equal mixture of two different compounds, but they're mirror images of each other, just in a 50-50 mix. Okay, so we know that two enantiomers are going to have identical physical properties to each other. So like this by itself has the same melting point as this by itself. Weirdly though, when I make the racemic mixture, I do 50% of this, 50% of that, the melting point is often going to be different than it was for either individual enantiomer. So physical properties of the racemate are different than they are for a pure enantiomer. Okay, so the reason for that, I guess like anytime we're looking at handedness and chirality stuff, like anything that's like a chiral or non-symmetric piece of clothing is a good analogy. I think the book actually uses like if you got a huge box full of left shoes and a huge box full of right shoes, they're probably like packed together in exactly the same way, like if they're all the same copy of the same shoe. But if you have a big box of like half left shoes and half right shoes, they're probably packed together in a slightly different way and not like fill space the same way or not have the same intermolecular inter-shoe attractions. Yeah. But they're going to interact with each other like differently than they did with other copies of their own identical selves. Question?
So the physical properties change specifically for the racemic mixture, but what about when there's other proportions?
Same thing then too, and they're actually going to change like, you know, if I had 25-75, that would also have different physical properties than either pure enantiomer or than the racemate. So it is usually going to change smoothly, but it might not be a linear, it might be like on a curve kind of a thing. Okay, so for reasons that we'll cover in the next chapter, it turns out that a lot of the time it's easier to make a racemic mixture of two compounds, like if you're starting from some other molecule, than it is to make just one enantiomer or the other. And so a lot of the time you can actually buy from chemical catalogs the racemic mixture for way cheaper than you can just buy like the pure R or the pure S. Okay. So one last thing we're going to cover here as far as like quantifying actual amounts of chirality. So what if we have a non-50-50 mixture? So we can describe with what's called enantiomeric excess. Or lowercase e for short. So this is just like percent of the more prevalent enantiomer minus percent of the less prevalent enantiomer. Or in other words, the percent of the major minus percent of the minor. So if you've got like 60% R form and 40% S, that's going to give you 20% enantiomeric excess. 20% specifically R, in enantiomeric excess. So this is actually, and again, we'll look at like stereochemical outcome of reactions at the end of the next chapter, but this is actually a great way to compare like how good is my reaction for targeting one particular enantiomer over the other as like the product of whatever you're doing. So the higher the enantiomeric excess is, the more you're favoring one particular handedness of molecule over the other, and the more selective the reaction is for that handedness. Okay. So, so there's a few sapling questions that ask you to do calculations on this, and it really helps for some of them to remember that racemic mixtures are always optically inactive, and so all they're doing is just like acting just like any other achiral solvent or whatever, and so it's only the excess part that's actually rotating the light, like having 20% more of the R is the only part that's left over to actually rotate the light. The rest of the 40% of here just cancels out with the 40% of the S. Okay. Questions about that? Yeah.
So the non-equal mixture has different physical properties, but still rotates light?
It does, yeah, but not as much as it would if it were like pure R or pure S. So this one is going to rotate light 20% as much as like the R form would have. Yeah. Okay. So any other questions about this before I wrap up this chapter? Okay, I'm actually going to take a minute and erase the other side of the board real quick, so if you guys want to think of anything. Okay. So just to sum it up, this chapter we covered a lot of new terms, and it's kind of tricky to figure out like which one applies when. So this one I'm going to do sort of a summary thing for this chapter. So the terms that we saw are chiral, which means lacks an internal mirror plane of symmetry, which means that it's not superimposable on its mirror image and it has an enantiomer. Okay, so those three things always go together. If it doesn't have the internal mirror plane, it's not going to be superimposable on its mirror image, which means that it and its mirror image are two enantiomers of each other. Another term we saw is asymmetric carbon, which is any C with 4 different groups attached. We also saw Stereocenter, which is any place where swapping 2 groups gives you a different molecule. And finally, we saw optically active. Which means it rotates light, polarized light. Okay, so these 4 things frequently go all together. Like something that's chiral will usually have asymmetric carbons, which are the most common type of stereocenter, and it will also be optically active. But we've seen examples where a molecule can tick some of these boxes but not others. So for example, if I say this molecule here, but I also put RAC in parentheses next to it, it's a racemic mixture of this plus the mirror image that I didn't draw. I'm just doing a little disclaimer, this is a racemic. So it's chiral with asymmetric Cs, which are stereocenters, but not optically active. So racemic mixtures are one way to screw with having all 4 descriptors go together. Another way to mess with it is with mesoforms. So this one is, it's got asymmetric carbons and stereocenters. But it's achiral and therefore optically inactive. Okay, so that's a good place to stop. I guess if you have any questions about this, I've got an office hour 2 to 3 today, and then if I'm in my actual office and I'm not busy, you can drop in. I probably will be busy this morning because I haven't finished writing the exam yet, but later today I should be able to talk if you come by.